And now I'd like to introduce today's speaker, Dr. Greg Fisher.
Thank you, Gio. And I'd like to say good morning to those of you joining us from the Americas, and good late afternoon to those of you joining us from Europe. And as Gio mentioned, I'll be talking about helpful hints and guidance for TOF-SIMS data reduction and interpretation. And many of you are new users of TOF-SIMS, and some of you are more seasoned users of TOF-SIMS, but I think these helpful hints and guidance for those of you that are new will be quite helpful. For those of you that are more experienced, might be good reminders of things that maybe you've forgotten. And just a little bit of history on this. Physical electronics used to have 10 helpful hints and guidance. And over the last 5 or 6 years, just interacting with new customers, we've added 10 more helpful hints and guidance to this presentation, just based on things that customers have encountered as they're learning TOF-SIMS. And I think it would be a great to share some of that information with a broader audience. And for those of you that are interested, in a few months' time, we will have a follow-on presentation to this that will talk a little bit more in detail about experimental setup for TOF-SIMS analysis. But that'll be another presentation. For now, I'm also going to turn off my camera during the presentation, and then I'll turn my video camera back on for the Q&A part, because I think it's a little more comfortable if you can see me. So we'll get into the presentation then. And so the first hint is shown in slide number 2. Also, if you do have a question, as Gio noted, you can post your question in the Q&A section on the Zoom, and all of the slides are numbered. So if you have a question with respect to a certain slide, it would be helpful if you put the slide number also. So the first thing that you will more than likely encounter right away in TOF-SIMS analysis is that you will see certain peaks that are very intense and other peaks that are very weak. And it is easy to assume that because you have a large peak, that means that most of your sample is composed of whatever that peak is. And that is not the case in TOF-SIMS. There are many matrix effects in TOF-SIMS analysis. And if we look at this table here, what we're showing is, as a function of atomic Z number, how the ion yield changes across the periodic table. So down at the bottom here, lithium, sodium, potassium, cesium, these elements have a very high ion yield in the positive ion polarity, and generally a very low ion yield or 0 ion yield in the negative ion polarity. On the other hand, elements like oxygen, sulfur, chlorine, bromine, iodine, these all have very high ion yield in the negative ion polarity and very little or none in the positive ion polarity. So the thing here to remember is that just because you see a very intense peak doesn't mean that is the majority of your surface composition. So these ion yields can also change as a function of matrix composition. So that means that if you're looking at oxygen in a silicon matrix, the ion yield of oxygen and silicon might be very different in a metal, for instance. Hint number 2. So when you're looking at your mass spectrum, you will see a nominal mass. So what we call the nominal mass in this particular case is 29.00. And inorganic ions generally will show up on the low side of nominal mass, and organic ions will generally show up on the high side of nominal mass. And this is true for both polarities. And it really has to do with the fact that most elements, their exact mass is less than nominal. So silicon, we generally say silicon is 28, but in fact it's 27.95 something. Hydrogen, on the other hand, has a mass of 1.0079, so it's on the high side of the nominal mass. So the more organic character you have in an ion, the higher it will be from nominal mass. And so here's a couple examples. Here's another one at a nominal mass of 45. Again, we see silicon hydroxide at the low with a mass deficit, and we see the organic fragment ion with a mass surplus. And keep an eye on the intensity of this silicon hydroxide peak. So this data that we're looking at in slide 3 is from the positive ion polarity. Now, if we look at the negative ion polarity, for instance, just coming back to the silicon hydroxide peak, notice that the intensity here is very low. The silicon hydroxide peak very heavily favors the positive ion polarity. You will see a little bit of it in the negative ion polarity also. So just be aware of that. But again, here we have an acid fragment ion showing up right about nominal mass. In the top panel, we see chlorine 37 showing up with a mass deficit, and this C3H minus peak showing up just on the high side of nominal mass. So again, elemental or inorganic ions will have a mass deficit, while your organic ions will have a mass surplus. Energy spread affects the peak position, and this is particularly critical when you're looking at atomic ions. So if you look at an atomic ion, say at a nominal mass of 27, and you're looking at your copper grid on aluminum tuning sample, and it's very common to look at mass 27. And what you'll see is that on the low side of nominal mass, you'll see the aluminum peak. And on the high side of nominal mass, you'll see the C2H3 peak in the positive ion polarity. And you'll notice that the aluminum peak is always broader than the C2H3 peak. And the reason that you see that difference is because atomic ions have a very broad energy distribution, which broadens the peak. As you go to multinuclear peaks or multinuclear ions, that energy distribution tightens up. And that's shown in a schematic illustration here on the left. And on the right, I've used an image from one of Arnold Delcourt's publications back from 1998 in Surface Science, where he and his group have mapped out the energy distributions for silver, silver dimer, and silver trimer. And you see, even for the trimer, that energy distribution is 15 or 20 EV. But if you look at this series of organic ions, those energy distributions are about 3 EV, full width half max. So the energy distribution affects both the mass resolution and also can have an effect on the peak centroid position. And that peak centroid position can have a big impact on your mass scale calibration. So some of you might notice that if you calibrate your mass spectrum using organic ions, then the peak assignments for your atomic ions or your inorganic ions become a little more unstable or a little more difficult. Conversely, if you calibrate your mass spectrum using inorganic ions, then the organic ion peak assignments can become more difficult. And this has all to do with those differences in energy spread. Now, fortunately, on the the TRIFT-based mass spectrometer. So whether you have an older TRIFT instrument or whether you have one of the newer parallel imaging MSMS spectrometers, you have this capability to optimize the mass accuracy using the Matsuda voltage so that you can achieve good calibrations on both inorganic and organic ions. So we have, I won't go into the details here, but we do have an application note, rather it's a technical bulletin that illustrates how to do that and gives you directions on how to achieve that. And this is really important because if you get better mass accuracy in your calibration, then it's easier to do peak assignments for both organic and inorganic ions. So what I'm showing here is on the demo system, of course, we've gone through this procedure of fine-tuning the Matsuda voltage. And then what you see here in this calibration is we have a number of organic ions as well as inorganic ions in this calibration. And across the mass scale that we've calibrated, we have less than a 5 ppm average mass defect, which is quite good for TOF-SIMS. In fact, it doesn't really get a whole lot better than that. Normally in TOF-SIMS, once you start getting above a mass to charge ratio of 100, typical mass defect of 20 to 30 ppm might be more expected. Okay. Peak ID. I'm having a hard time getting rid of this. All right. So one thing that you can do in doing some of your peak assignments is using a properly calibrated mass spectrum to help look at some of your higher mass peaks. So one of the things that I will often do is I will calibrate my mass spectrum using 3 peaks at low mass. And then often I will go up to some of the highest mass peaks that I see in my mass spectrum, and I will open up the peak ID tool. And based on the compositions that I see in that peak ID tool, I think I suspect what the composition might be. And if it is that composition, then I should be able to include that peak in my calibration, and the calibration will still stay quite good. If it is an incorrect peak assignment, it will cause your mass scale calibration to get worse. And so that would be an indication that it is a bad peak assignment. So you can do this for a number of peaks in the mass spectrum, and you can use some knowledge that you have about the sample, about whether it contains nitrogen or sodium or other elements, and that can help you in assigning your peaks, coming up with putative peak assignments. But the mass scale calibration can be quite useful in deciding whether it's a reasonable peak assignment or whether it's a poor peak assignment. And then you can carry that one step further. And so if you think that you have a good peak assignment based on the calibration, then you can also use the isotope tool that's built into the software, and you can put in a formula for that peak. And what the isotope tool will do is put markers on your mass spectrum of what would be expected if that is a correct peak assignment. So here we have in the green markers is the calculated isotope distribution for a composition of C26H56N. And that looks like a very good fit. And so that gives another level of confidence in that peak assignment. Isotope distributions are also quite useful for looking at elemental samples. So this particular example is from a solid oxide fuel cell that have a number of elemental components in the matrix. And this is showing the isotope, the expected isotope distributions for strontium, yttrium, which has only a single isotope, and also the zirconium elements. So I would add, just as a precaution, in the isotope tool in the software, you can only do one set of elements at a time. So you would see either the strontium or the zirconium or the yttrium. It wouldn't give you all three of these calculated distributions at the same time. All right, hint number 6. If you are looking for a molecular ion in the positive ion polarity, more times than not, that molecular ion will show up as the M+ hydrogen positive ion. So the hydrogen carries the positive charge, it attaches to the molecule, and you'll get an M+H ion in your mass spectrum. Similarly, if you are looking for a molecular hydrogen in the negative ion polarity, more times than not, it will show up as the M-H negative ion. A very, very common surface contaminant that is quite easy to see in TOF-SIMS is silicones. And more often than not, it is PDMS, or polydimethyl siloxane. PDMS is present in most adhesives. So we recommend that you not use carbon tape, copper tape, and if you need to use tape for securing fiber samples or powder samples for analysis, there is one very specific brand of double-sided tape that has essentially no silicone residue, and that's what we recommend for use. We can get that information to you if you would like it. But the thing about PDMS is that very little results in very large peaks in your positive ion mass spectrum. So you can have essentially, almost no PDMS on your sample, but you will see very intense peaks at 73, 147, 207, 221, 281, 325, and so on. The other deleterious effect of silicones, in particular polydimethyl siloxane, it is that they are quite mobile in a vacuum environment. So even though your tape is underneath your sample, the PDMS will migrate to the surface of your sample. So it can be a problem. If you encounter this, just clean your sample holders and your tweezers and your other tools with isopropyl alcohol, and that'll get rid of it. Characteristic silicone fragments, generally when you look at the mass spectrum, so this is the C3H9Si peak at a mass to charge ratio of 73, a nominal mass of 73. And you'll generally notice that it has a tail on the high mass side. And this is a very typical observation of some of these silicone fragment ions. And it is due to the fact that the larger ions will fall apart in the field-free region of the mass spectrometer. And those have a lower kinetic energy than the ion that shows up at the correct mass to charge ratio. So anyhow, some of those, the post-source decay will give this tail to the high mass side. So that's a very common observation. Also in TOF-SIMS, many of the typical rules for interpretation of mass spectra still apply. So probably the biggest one is the nitrogen rule. So what the nitrogen rule says is that if you have a peak in the positive ion polarity that shows up in an even mass, then it is quite typical that that ion will contain an odd number of nitrogen atoms. So here we're looking at a peak at a mass to charge ratio of 268. It is the M plus H ion, and it is bearing one nitrogen atom in the molecular structure. You can confirm the presence of nitrogen in your sample by looking at the negative ion polarity. And if there is nitrogen present, you will see a fairly strong peak and a mass to charge ratio of 26. So this is the CN minus peak in the negative ion polarity. So a good confirmation that your molecular ion in the positive polarity might contain nitrogen. Phthalates and polymers and additives will almost always produce a secondary ion at a mass to charge ratio of 149 in the positive ion polarity. And this peak has this structure. So phthalates will almost always give a peak at a positive ion peak at a mass to charge ratio of 149. Phosphates will produce secondary ions in the negative ion polarity at a mass to charge ratio of 63 and 79. So here we're looking at a sample of tricresyl phosphate. And so we see the C6H5O ion, and we also see the PO2 and the PO3 from the phosphate group. So those will always be very strong, pardon me, very strong intense peaks. Similarly, for sulfate chemistry, you will always see a peak in the negative ion polarity and a mass to charge ratio of 64 and 80 and 97. And these are the SO2, SO3, and HSO4 ions. It is not always the case that you will see an intense sulfur peak. But for sulfates, you will always see strong peaks at 64, 80, and 97. Fatty acids are quite common in many samples and can be present in several different types of adhesives. The good thing about fatty acids is that they are not mobile in a vacuum environment like silicones are. So if you see fatty acids on your sample surface, it could be inherent in the sample, or it could be that your sample has come into contact with something that has put fatty acids on the surface. And I can tell you that the most common source of fatty acids on your sample surface is by somebody handling your sample with their fingers. You have a lot of oils on your skin, and that is quite easily and readily transferred over to your sample surface and will actually make it very difficult to see the chemistry of interest if that's happened. But a number of fatty acids will give peaks at 227. The most common are palmitic acid at 255 and stearic acid at 283. Again, these are in the negative ion polarity. So these are the M minus H molecular ions of these fatty acids. So sometimes you want to differentiate between molecules that have similar structures, and this can be a little more challenging. And so here we're looking at mass spectra from glycerol monostearate in the top and stearic acid in the bottom. And so stearic acid, of course, gives a strong peak at 283. Glycerol monostearate gives strong peaks at 283 and 255. you know, there could be the possibility that this 255 is lauryl acid and not glycerol monostearate. So we want to dig deeper into the spectral data to see what else we can find. So then we might look at the lower mass to charge ratio. So this again is the negative ion polarity. This is the positive ion polarity. And we see that at low mass to charge ratio, the peaks are very similar, and it would be very difficult to differentiate stearic acid from glycerol monostearate without using something like multivariate analysis. So let's look more closely at the data and see what else we can find. So if we look at higher mass to charge ratio, what we can see is that glycerol monostearate has a very different fragmentation pattern than what we see for stearic acid. So this is the positive ion polarity. If you remember, for stearic acid in the negative ion polarity, we see the M-H at 283. In positive ion, we see the M+H at 285. And then we see the M-OH, still a positive ion, at 267. But for the glycerol monostearate, we see a very different fragmentation pattern. So this would distinguish between a combination of stearic acid and palmitic acid, and gives us very clear evidence here that we're looking at glycerol monostearate. So digging deeper into the spectral information can give a lot of information and help us choose what we're looking at. Fluorocarbons. Fluorocarbons give very dominant peaks in the positive ion polarity. So even for carbon at a mass to charge ratio of 12, we see the CF peak at a mass to charge ratio of 31, CF2 at 69. We see a number of very strong peaks. Now these spectra are from two different structures of fluorocarbons, and we can see that the fragmentation pattern is different for those two fluorocarbon species. And so it takes a little bit of work to differentiate which molecule you're looking at. In this case, we're looking at two slightly different structures, but they are both polyether fluorocarbons. For polymers, it is almost impossible to see the molecular ion for polymers. They're generally just too massive to see by TOF-SIMS. TOF-SIMS, of course, is very energetic and causes a lot of fragmentation. And so it's you would never see a polymer molecular ion at 20,000 or 30,000 or 100,000 Daltons, for instance. But very often what we will see in the TOF-SIMS spectrum is the monomer unit for the different polymers that we're looking at. So in the top is the low mass to charge region of polystyrene, and we see very clearly the C7H7 monomer. In the bottom spectrum, this is the low mass region for poly 2-vinyl pyridine, and we see this vinyl pyridine monomer group here at a mass to charge ratio of 106. Again, I'll just bring us back to the nitrogen rule. In the positive ion polarity, we're looking at a peak with an even mass, which often indicates an odd number of nitrogens in the ion. And in fact, here we see that. We have a single nitrogen atom in this even mass ion. When we're looking at polymers, it is pretty characteristic also when you're looking at some of the monomer units that you will see a shoulder on the low mass side. Again, this is due to decomposition of the ions. In this particular case, the decomposition is happening in the extraction region, and so these decayed ions have a slightly higher kinetic energy than the main peak ions, and so we see this shoulder at lower mass. So this is not an uncommon observation. So, and the reason that I bring these two examples up of the high mass shoulder for the silicones and the low mass shoulder for some of the characteristic aromatic ions is because if you're looking at these and you're trying to optimize your sample bias for an insulating specimen, you might look at this and say that your sample bias isn't quite correct. But what I would recommend is that you look at other ions and make sure that the peak shape is symmetric to get your sample bias correct for that insulator analysis. Sometimes it can be misleading to look at some of these aromatic ions for that. Oligomeric distributions can be observed by TOF-SIMS. So I just mentioned a couple slides ago that it is very rare, if not impossible, to see intact polymer ions for a lot of low molecular weight oils or other contaminants. Because of the impurity, in some cases, what you will see is a very broad distribution of peaks. And this could lead you to a conclusion that, gee, there's something wrong with my analysis, something isn't working right. But I can assure you that if you're seeing a very broad distribution of ions, it is more than likely an oligomeric distribution from some oil or wax that's on the surface. And so this is, you know, not uncommon depending on the type of sample that you're looking at. So don't be alarmed if you see such a feature in your mass spectrum. And you can even see these with quite high molecular weight polymers, and you'll see several repeat units of these types of oligomeric distributions as you go up in mass to charge ratio. And lastly, I wanted to cover some potential sputtering artifacts. So if you're doing three-dimensional imaging or just doing a straight depth profile of your sample, sometimes the sputter beam that you use by default isn't the best sputter beam for that sample. And here I show just one example. There's many different examples that could be discussed. But in this particular case, we were looking at a 6 micron thick aluminosilicate aerogel. And we were trying to depth profile that film. The anticipated or the expected composition was a uniform silicon to aluminum ratio. And so, of course, our default sputter beam being monoatomic argon produced this sputter crater that was dark at the bottom, and that depth profile is shown here by the dashed line. And we see that as a function of depth, the silicon to aluminum ratio changes. So we switched over to use C60 sputtering, and I used the 40 keV C60 double plus ion for sputtering. In this case, we see a nice reflective sputter crater, which indicates that the crater bottom is quite uniform and has not roughened as a function of depth. And if we go back and look at the data, we see as a function of depth that the silicon to aluminum ratio is quite uniform. So that is our 20 most common helpful hints and guidance for TOF-SIMS data interpretation and data reduction.